Okay. Okay, so we start with registration. Okay, welcome to this new lecture of the machine learning course. Okay. And actually, okay, so what we will do now is to finish the part related to linear classification approaches. And then after this, we will start with the part of theory. And so we will start dealing with the theoretical aspects of machine learning. Last time we talked about logistic regression. Okay, welcome. Seen that logistic regression is. Sorry, can you mute the microphones? Okay. So we have that logistic regression is a generalized linear classification model because you have that in logistic regression you have that the inputs are linearly combined through some parameters W in order to obtain a number that then is provided as argument to a logistic function. And the output of the logistic function is a number between 0 and 1, which encodes the conditional probability of observing a particular class given the input data observed. We have seen that actually this model is nonlinear in the parameter W's because you know that the logistic function is a nonlinear transformation. But what we have seen is that actually the separating surface introduced by this kind of model is an hyperplane. So you have that the instances of one classes and the instances of the other classes are separated by the logistic regression by an hyperplane, where this hyperplane lies in the feature space. So in the space defined by the features that you have defined. And you have seen that even if you use an hyperplane in the feature space, this separating boundary between the instances of one class and the other class may be highly nonlinear in the input space according to the features that you have used in your problem. We have seen also that actually, differently from linear regression, we do not have a closed form solution for logistic regression, but we have seen that we can compute the gradient and that actually the optimization problem that we have to solve is a convex problem. And so by following a gradient ascent approach, we can actually find the global optimum of the problem. So we can find the parameters W that minimize your loss function, that as we have seen, the loss function was generated by the negative log likelihood of the data. So by minimizing this loss function, you are maximizing the likelihood of the observed data given the parameters of your model. And you have also seen that actually the gradient is what is reported here in the slide. The gradient has a familiar shape because actually it's very similar to what we have seen also for the gradient in linear regression. You have the summation over all the samples of the error, so the difference between the model prediction and the true output, that in this case, being a binary classification problem, can be 0 or 1, that is a Tn, multiplied by the vector of the feature associated to the example n. So this is how you can compute the gradient of the loss function, and in this way you can find the parameters that maximize the likelihood. Good. Then, few things more. We have that if you want to apply logistic regression in a problem where you have not only two classes, but you have multiple classes, actually you can use a generalization of the logistic function that is the softmax function. You see the softmax function in the equation. Here you see how you can express the probability, the conditional probability of observing class K given the vector of features phi. And you see here that is actually the ratio between the exponential value of the linear combination of the weights for class K in scalar product with the vector of feature phi, divided by the summation over all the classes that you can have in your problem. So we are dealing with multiple classes here of the same quantity. So the exponential of the scalar product between the weight vector for class J and the feature vector phi. As you can see, of course, this guarantees this is a normalization and guarantees that the probabilities, the conditional probabilities sum to 1. If you try to rewrite this formula for only two classes, actually what you get back to the logistic function that we have seen in the last lecture. So this is the softmax is the generalization that you can use when you have multiple classes. So when you have multiple classes, you can represent your model in this way. And so how to train this model, as we will see, actually the training of this model is very similar to the training of the two-class logistic regression model. Here you find the likelihood, so the likelihood of the observed target metrics, because now we have multiple classes. And so, as we have seen, we translate the fact that you have multiple classes in using the one-hot encoding. And so you produce a vector whose size is the number of classes, and then you put 0 or 1 in this vector according to the case in which the sample belongs to one class or not. And so we see here that actually the likelihood is the same that we had in the previous case, with the difference that now we have to generalize to more than two classes, and so now we have k classes. So we have another product. So we have the product over the samples, that is the product indexed by n, and then we have the product over the classes that is indexed by k. And so here you have the likelihood of the model, where y and k is exactly the probability of observing class k given the feature of this example n. So how to optimize this likelihood? Actually, exactly as we did for the two-class case. So we take the negative log likelihood, and we have that the two product becomes two summation. And so we have a minus the summation over the samples, and then we have the summation over the classes of the expression that we find here. If you take the gradient of this negative log likelihood, you get this case. Pay attention that now the loss function is a function of the weights, and the weights, you have a set of weights for each class. So we have the weight for class 1, that is W1, the weights for class 2, W2, and then up to the weights of class K, WK. So here, in the last line, you see reported the gradient of the loss function only with respect to the weights of class J. But of course, you have also to consider then the gradient with respect to the weights of all the classes. And you see that actually the gradient of the loss with respect to the weights, the parameters used for one class is exactly the same that we have seen before. So the summation over the examples of the difference between the model prediction for this sample using the weights of class J minus the element of the target matrix at row n and column j multiplied by the feature vector of example n. So this is exactly the same gradient that we see before, specified for the parameters of class j. Of course, you need to compute the gradient of the loss function with respect to all the parameters, so the parameter of class 1, 2, up to class k, and then you will update these parameters according to the gradient that is reported here. And again, you will find the parameters for all the classes, and the problem is still convex, and so you are sure that you can converge to the global minimum of this loss function. Finally, I want to highlight the relationship between the logistic regression approach and the perceptron algorithm that we have seen before. And you can see that if you replace the logistic function with a step function, so the logistic function is the one on the left, the step function is the one on the right, you see that actually the step function is a limit case of the logistic function. Because actually, if you multiply the input for a very large number, actually what happens is that you see that the logistic function becomes closer and closer to a step function. And actually, if you do this change, but you see that actually the update that you can have to the parameter is exactly the same formula. So the parameters are updated by the difference between the model prediction minus the true value multiplied by the feature vector. So actually is the very same update. The difference is that, of course, by the logistic regression approach, by using the logistic function that is smoother, removes the problem of instability that, of course, you have when the points are not linearly separable using the perceptron, because we have seen that when the points cannot be linearly separate in your feature space and you use the perceptron algorithm, the problem is that you never terminate the update. While using the logistic approach, actually, you have a point of minimum that, of course, will produce some misclassified points, but is still the solution that maximizes the likelihood of the data given the parameters of your model. Okay, so this, in a sense, concludes this first part of linear models, models for linear regression and models for linear classification. So they are very simple models, but pay attention that they are also very effective models in many applications. Of course, their main drawback is that they require knowledge of good features from one side, or if you have not knowledge of good features, you have to try to use many features. But in this case, when you use many features, we have seen that the risk that you have is that you will overfit the data, because you are using a model with a lot of parameters, and so your hypothesis space is very large, and so you have to pay attention if in the case where you have many parameters and few samples. In this case, you have the risk that your model will learn not the model, but actually will learn the noise over the data, and so will fail in providing good predictions. So, since now we have these basic tools, so the tools for linear regression and linear classification, is the time to go deeper into the theory of machine learning. And with the theory, we will see some basic concepts that are useful also for more complex methodologies for doing supervised learning. And while we'll do the theory, I have the possibility of doing examples with these basic tools. So now I will go to the theory. Okay, so we start talking about the no-free-lunch theorems. Actually, no-free-lunch theorems are very popular theorems in machine learning, and actually they are quite disturbing theorems. Now I try to state the theorem, and you will see that these theorems are very strange. You say, what they are saying? They seem very bad theorems. So there are many no-free-lunch theorems. Now I just state one of the many no-free-lunch theorems. They are all very similar, the one with the others, so they are almost the same. Now I assume that we are in the setting of classification with only two classes. So we are in the setting of binary classification. And what I want here to analyze is the following terms. So in particular, we want to put the attention on the accuracy, generalization accuracy of a learner L. So capital L is a learner, and the accuracy of this learner is the performance of the learner over samples that were not used during the training. So you have a data set that is used for training. You take this data set and you train your learner. Then you want to know the performance of the learner over a new data set that is different from the one used for training. And in particular is the set of all the data that were not used for training. So suppose that you have a space of possible inputs, you have used some inputs for training, and then all the other inputs, so all the non-training examples, are used to evaluate the accuracy of your learner. Of course, you are pretty interested in this performance because it's the performance, the accuracy of your learner is the performance that you will have once you will use the learner over new instances. Then we define the concept of, as you can see here, calligraphic F. This is the set of all the possible concepts. The term concept is used in classification to mean the function. So capital F is the set of all the possible function that you want to learn. And in this case, in particular, is the set of all the possible function with a binary output defined over the input space X. Perfect. Now let's see what the theorem says. The theorem says there is a question. The learner would be like the loss function. No, the learner is an algorithm that you use, whatever algorithm do you want, an algorithm that learns a model. So you can see the learner as a model, learned over the training set. For instance, suppose that we are doing logistic regression. Actually, the learner are the parameters that you learn for your logistic regression model. F is basically the hypothesis space, right? No, is more. F is the space of all the possible hypotheses. Not only the one used by your learner, but is the space of all the possible functions. If you recall the plot in the very first lecture, you can remember that it was the space of all the functions, and then the hypothesis space is subspace where you search for the best hypothesis. Okay? No, F is the space of all the functions. Now, the theorem says that for any learner, this is important, it's not important which kind of algorithm are you using for learning of data. For any learner that you choose, actually, the average accuracy of your learner over this classification problem is 1/2, so it's a half. And you know, having an accuracy of 0.5 in a binary classification problem means that your learner, whatever it is, your learner, is random. Because of course, if you have accuracy 0, it means that you make a mistake for any sample. If you have accuracy 1, it means that you perfectly classify all the samples. If you have accuracy 0.5, it means that 50% of the time you make a mistake. Okay? But actually, having such a performance means that you are random guessing about the class. So, and pay attention that this is true for any distribution of the data that you have in input and for any size of the training set. So it's not a matter of that you have too few data. Even if you have a lot of data, you have this. So as you can imagine, actually, this result is quite disturbing because so we are doing all this stuff here, all the course, all this complex mathematics. We are investing billions of dollars in research in machine learning, and then we have a theorem that says that any learner cannot have an average performance that is better than 0.5. So any learner cannot be better than random guessing. Of course, you will agree with me that actually this result is quite strong. So, but okay, the result is I'm not cheating, this is the correct result. But where is the point? So why we have not to worry too much about this? There is a question. A learner L learn only one concept. Yes. So we have one concept that needs to be learned. So the samples in our training set comes from one concept, but of course then we have to consider different things. This is independent of the dataset used for training L. Yes. Other question. The theorem is considering all the possible functions. Yes, and this is actually the point. Actually, not all f in f are equiprofessional. Exactly. This is the main point. So the main point of this theorem it says that any function in the world, any function that you can imagine, has the same probability of being the function that I have to learn. If this is the case, the theorem is true. So if any function is actually possible, what you observe from the data is useless for predicting what you do not observe, because since any function has the same probability of being the true function, observing a data in one point is useless to predict the value of the target variable in another input point. And so you have no hope in that case. So machine learning is based on the implicit assumption that actually not all the functions, all the possible target function, in this case, all the possible concepts, have the same probability. But we assume, in most of the cases implicitly, other times explicitly, we assume that actually there is some kind of regularity in the concept that we are going to learn, in the sense that it is more likely that the true function that we have to learn belongs to a class with respect to belong to all the possible space. For instance, we assume that the true function will be somehow smooth, with not too strong variations, so that I can learn and I can generalize the knowledge that I gather from one point also to the surroundings. So this is implicitly an assumption that I'm doing that say, okay, if two input points are similar, their output will be similar. And this is what I try to leverage in order to use this kind of supervised learning algorithm. But if this is not true, if actually any function can happen, this means that you can do machine learning in this case. Because, of course, the only information that you have on the problem is the sample that you observe. And if this sample have no correlation with what happens elsewhere, of course, it's useless to observe them for predicting what happens elsewhere. Okay, so this is the point. There are no flange theorem, not only for classification, there are no flange theorem for any field of the machine learning case, but because actually the machine learning approach is based on the assumption that not everything can happen. But we live in a world that is somehow compressed, in a world where only some particular things can happen, in a world where there is some level of regularity in what happens. And we also, as humans, exploit this assumption when we operate in the world. We assume that actually the world will follow some rules. The physics exists, for instance. We use the physics of our world. But if I take you and I move you in a world where no physics laws exist, of course you will have problem in taking decisions because you are not able to predict what will be the outcome of your decisions, action, and so on. There is another question. So we assume that the points inside the dataset are ID, but implicitly we remove this assumption to find just one learner. No, actually, we do not remove the assumption that they are actually they are IID. even if in some cases we even do not make this assumption. We simply assume that remove the noise that you have on the points, but simply the function that we are going to learn as some regularity. I'm not putting the attention here now on the stochastic properties of the noise affecting the samples. I'm just saying that there is some relationship between the input variables and the target variables, okay? And this relationship has some regularities. Okay? Usually the noise affecting the sample is always considered as independent. This is always assumed. Okay, so now we have this strong result, but okay, keep calm. It's not a tragedy. It's nothing. It's something important from one side, but is not. So the message is important, but the consequences are moderate. How we can prove this is not really interesting, but actually, of course, it's quite simple to see if you are able, if you have a learner that for every concept that you can imagine F has an accuracy that is a little bit larger than 0.5, then for sure you will be able to build another concept F prime where the accuracy is 0.5 minus delta. In my opinion, the best thing to do to understand the proof is the following. Suppose that you have an input space with size n. So the input space can have only n different values. And suppose that you have a dataset of n minus 1 values. Perfect. So now over these n minus 1 samples, you can build the learner that you want. So you can build the model that you want. And this model will make a prediction over the only single point that you do not observe. Of course, if any function is possible, this single point that you do not observe can be of class 1 or of class 2. And if all the concepts that I assume that is perfectly over the remaining n minus 1 point, if all the concepts have the same likelihood, the same probability, there is 0.5 probability that the sample that you do not observe is of class 1 and 0.5 that is of class 2. And so any model that you will learn will have an average accuracy of 0.5. Again, because even if you have seen n minus 1 sample over n possible sample, but if there is no relationship between what you observe and what you do not observe, even if you have not observed only one point, this point can have any value, independently from the value that you have observed in the training set. So it's not a matter of overfitting, it's not a matter of how many samples you observe. It's simply a matter about the regularity of the function that you are going to observe. There is another way. Why it comes to lunches maybe is clearer in this second wave, in another theorem of no free lunch theorem. The corollary that you see here, that says that for any two learners, so now take two different algorithms, L1 and L2. The corollary says that if exists a learner, a learning problem in which the first learner is better than the second learner, so for sure it will exist another learning problem where the second learner is better than the first learner. So there are no free lunches. So there is no algorithm that rules out all the other algorithms. There is not algorithm that is better than all the other algorithms. Because if there is a problem where an algorithm is better than the other algorithm, so then there will be for sure another problem where the vice versa happens. So what he's saying here is that actually there is no single approach that can dominate everybody. It depends on the regularity of the concept that I'm going to learn and on the assumption that my learner, so my learning technique, is making. So what is the take-home message that you have to learn is that don't expect that your favorite learner to always be the best. So this is very common in machine learning. So people use techniques, see the performance, and say some techniques in some problems are very good, and so say, okay, so this is the best technique, and so the other techniques are not interesting because I have experienced that this was very strong technique. And actually, this is actually a problem to reason in this way, because maybe that technique was really good in that class of problems because that technique was able to capture the regularity of that class of problem. But if I move in another class of problem, maybe other regularities are important that are not easily captured by these techniques. There is a question, so learner is any machine learning algorithm? Yes, actually. A learner is a learner, so a learning technique. So if you use neural network, and neural network, for example, works very well in image classification, this doesn't mean that neural networks will work very well for other problems. Work well for that kind of problems. If in some other problems regression trees are very good, okay, they are good in that problem, but maybe they are not good in other problem. So what is so the solution? The solution is that you cannot fall in love with techniques. You have to keep the distance. So unfortunately, as we are doing between us in these days, so we keep the distances, we have also to keep the distance with the algorithm. So the algorithm, you have to look at them objectively and not try to be a fan of one algorithm with respect to another algorithm, because they have different properties and work well or bad in different contexts. So the important thing is to know them, for sure. You need to have some experience, so you need also to try them in order to build a feeling with which are the problems where this technique works well and when it works not well. And so just to say that, as we have already said, it's not said that a more powerful, because actually there is no more powerful technique. It's not true that a more powerful, in quotes, is better than a less powerful technique, because there is no more powerful in general. So here the question is, but how could, say, a deep neural network be less accurate than a single layer one? Yes, it can happen that adding more layers is useless for your problem. Because again, maybe adding more layers and so building a network with many parameters is not really good, because maybe you have a few data and so you learn something that is noisier, and so a simpler model can work better. It depends. So now we try to go into more details in this problem and how I can understand if my technique is working at best or if I can improve it from a theoretical point of view. So now, we move to the concept of bias-variance trade-off that we have already mentioned in the previous classes, because actually was the central point in supervised learning. So supervised learning is solving the bias-variance trade-off. So being able to properly run a supervised learning algorithm means to be able to balance the bias and the variance introduced in the estimation of the parameters of the learning algorithm. So let's look at what we are talking about. So we now introduce this bias-variance decomposition for a particular case, that is the case of regression, but pay attention that actually this concept applies to all the field of machine learning, not only for regression. We apply to regression because it's somehow easier to show this decomposition, but actually it holds for almost all the fields of machine learning. Everywhere you apply some machine learning technique, you are somehow dealing with the bias-variance trade-off. So we assume to have a data set with n samples, and these samples are again obtained by a function f that is unknown. This is the usual setting that we have seen for regression. So we have that our target variable is produced by this function applied to some input vector x, and then we have a noise, a stochastic noise. We assume that the stochastic noise is zero mean, and we assume that the variance of the noise is sigma square. We are not assuming that the noise is Gaussian in this case. We are simply assuming that is with a zero mean, and sigma square is the variance of the noise. So we are in this setting here. Now, what we want to do, we want to find a model, we already know this, a model y that approximates f as well as possible. And in order to evaluate the loss of the model y with respect to the function f, we have seen that we can use, for instance, the expected square error. In this case, in particular, we are considering the expected square error only on the input datum x. So we are not considering the loss over all the input space. We are just focusing on one single input. Of course, then you can generalize over all the input space, but just to take the things simple, focus on one point that was not in the training set. And now, on this point that was not on the training set, I want to evaluate what is the expected squared error. So the expected value of t, that is the true value for that point, minus what your model y of x predicts, all raised at square. So it's the square difference between the target value minus the model prediction. So this is the expected square error. So now we see that this term here can be decomposed in the following way. So first of all, we develop the square, and so we have t square plus y square minus the double product between t and y. So this is the first. Then we use, of course, the linearity of the expected value, and so we know that the expected value of a summation is the sum of the expected value. And so we have the expected value of t square plus the expected value of y square minus the expected value of the double product. Then what we want to do now is to highlight some variance terms. And in order to do this, we can apply a common trick. So first of all, you know that the variance of a random variable is equal to the second moment of the random variable minus the first moment square. So this is the usual expression for the variance of a random variable. So the variance of a random variable is equal to the second moment of the random variable minus the first moment square. As you can notice here, we have the expected value of t square. That is exactly the second moment of the random variable t. And in the second term, we have the expected value of y square. That is the second moment of the random variable y. Perfect. So now, in order to make appear the variances, I would like to have a minus the first moment square. But in order to not change the equation, I have to sum and subtract the first moment square. So as you can see here, I have the expected value of t square plus and minus, it says that I'm adding and subtracting in order to not variate the equation, the first moment square, and then I do the same trick, I'm summing and subtracting the expected value of y at square. So I am doing this operation for highlighting the variances. Then for the last term, I simply took the 2 out from the expected value, and then the value of t multiplied by y can be rewritten as the value of f, because the expected value of t is f, multiplied by the expected value of y. So I can take out 2t from the expected value, and by doing this operation, I can replace t with f. And I can do this because the noise epsilon, okay, is actually independent from our model y, since I'm considering a point that is outside from the training set. And so I have this expression here. Now I rewrite the terms, and so I have that the second moment of t minus the first moment of t square is the variance of t, and then I have plus the first moment of t at square. The same trick happens for the model y. I have the variance of y plus the first moment of y at square. And finally, I rewrite simply the last term, that is minus 2 times f multiplied by the expected value of y. Okay? So now rearrange the term, so I have the variance of t, the variance of y, and now I take the expected value of t squared, the expected value of y squared, and minus 2 times f expected value of y, and actually this is nothing else than a squared form, because the expected value of t squared, we have already said that the expected value of t is f, and so the expected value of t squared is f squared. So I have f squared minus 2 times f expected value of y plus expected value of y squared. And so this reduces f minus expected value of y at square. Okay, so what I've done is, starting from the expected value of the square difference between the target value and the model, I have rewritten this expected value as the summation of 3 terms. The first term is the variance of t, but the variance of t is equal to the variance of epsilon, and the variance of epsilon is sigma square. Sigma square is called the reducible error. So is the error that you make even when you know f, because you have seen that f is the true function. But even if you predict f, the target values that you see are obtained by summing f with the noise epsilon. And so the noise epsilon cannot be reduced because it's the unpredictable part of the function, it's the stochastic part. And so, for sure, your model will make a mistake that is at least a sigma square. So sigma square is the best that you can have, is the minimum error that you can have. So irreducible error. So we are not interested in this error. Why we are not interested? Because whatever you do, you will never reduce this error. What you can do is to reduce the other 2 components of the error. We have the variance of y. The variance of y is how much your model changes as a function of the dataset that you use for training. Pay attention that all these expected values variance are taken with respect to different realization of the training set. So the stochastic part here is that I am training a model with different realization of the training set, with a fixed sample size. And I'm saying that I have some kind of variance. When this variance will be high? This variance will be high when you have few samples and a lot of parameters, because you know that when you have a few samples and a lot of parameters, the prediction of your model is highly influenced by the sample that have been observed and used for learning the parameters. So this is the variance. So the variance of the output of your model with respect to, again, the realization of the training data. And then the last term that composes your error is the bias square. The bias here is the expected value between of the difference between the true function f and what your model predicts, raised at square. So this is the bias square. And when this will be high? This will be high when, in expectation with respect to the data set that you use for train, your prediction is in average similar to the true model. And when this is true when you have an hypothesis space that is very large, and so, okay, it's true. If you have a few samples, your model will predict very different things according to the dataset that you use. But in average, your prediction will be exactly the same as f. On the other hand, if you use a very small hypothesis space that unfortunately does not contain f, what happens is that even if you consider the expected value with all the possible realization of the training set, you will predict something that is far from the true function f, and so you will have a large bias. So summing up, you have that the loss function, so the square error in this case, expected squared error that you perform in some point x can be decomposed in three terms. Irreducible error, variance of t, that is not of your interest, and then two terms, the variance of your model and the bias square of your model. Of course, these are two terms that are interested because y is in our hand. We choose the parameters of the model y in order to reduce the error. What happens is that actually the variance and the bias square are in trade-off, unfortunately, because we would like to put both of them to 0. So we would like to have variance as 0 and bias square 0. But given a fixed size of the training set, what happens is that if you try to change something in your model to reduce the variance, usually what happens is that you are introducing the bias. On the other hand, when you are trying to reduce the bias, usually you introduce variance. So you have not to focus only on one of these two terms. It's not reasonable to try to minimize the variance or try to minimize the bias, because your error will be the sum of the two. And so you have to try to minimize the sum, not the single terms. While usually what people doing machine learning, doing supervised learning is induced to do is to try to minimize the bias, because it's the common case. Because when you see that your model performs poorly, you say, I want a more powerful and more complex method, and so I use more and more parameters. The result of this is reducing the bias, but this reduction in the bias will induce an increase in the variance because you will be more sensible to the noise in the data. So this is actually the main problem. You have to try to balance both of these. There is a question, since the bias is squared, does it mean that it matters more on the expected error compared to the variance? No, because also the variance is square. The variance, is a second order statistics, so both of them are square. But this is quite obvious because also we start from a square quantity, so the square, the loss function. And so all these terms, the variance of t, the variance of y, and the bias square are all square terms. Can we obtain something meaningful if we use just the average error instead of the average squared error? Meaningful if we just... okay, you can change, of course, the loss function. You can use whatever loss function do you want, but actually, what happens changing the loss function is that then you have to be sure that you are able to optimize this loss function, and so to find the model that minimizes the loss function. For what concerns the bias-variance decomposition, it holds for any possible loss function, any possible problem. It simply will change the formulation, will not be maybe like this, but you have always the possibility of taking a loss function and decomposing a part of variance and a part of bias. Okay. Okay, so here in this picture, actually, you see that a picture that summarizes a little bit this concept. So on the top left, left of this picture, you see a case where you have low bias and low variance. This means that you are you have a target and you are throwing darts to the target, and if you have a low variance and low bias, actually you are consistently good in centering the bullseye of the target, and so it means that you are very good. And this actually never happens because unfortunately you are never so good in the real world. On the other hand, if you look at the bottom right, you have a case where you are aiming in the wrong direction, and also you are very trembling, and so your darts are spread a lot. So actually you are throwing the darts blindly almost. Fortunately, also this is usually never the case. So you are never in such a bad case. Usually you are or on the top right or on the bottom left. So the top right is the case where in average, you are aiming at the bullseye, but there is a lot of variance because you are trembling a lot. So this is the case where you have low bias, but you have high variance. And so this is overfitting. On the other hand, on the bottom left, you are aiming consistently in the same region, but unfortunately, this region is not the bullseye of the target, and so you have low variance because you are continuously aiming at the same region, but the region is wrong, so you have high bias. And so this is the case in where you are using a model that is too simple, because okay, even if I change the dataset for training, I get more or less the same solution, but the solution is wrong because it's too simple. The model is not able to describe the phenomenon behind the data, and so you need to move. Unfortunately, if you try to move this cloud of points toward the bullseye, they will start to spread, as in the top right picture. So you have to try the compromise. So try to move them toward the red target, hoping not to increase the variance too much. Can we say that variance is related to the speed of convention with respect to the number training sample? We can say that differently from the bias is influenced by number of samples. So all these reasonments is made by a fixed dataset. So a dataset with a fixed number of samples. Of course, if you can increase the number of samples, this is always beneficial because by increasing the number of samples, the bias doesn't change, while the variance reduces, as we will see in a minute. High bias, low variance is underfitting, yeah. While low bias, high variance is overfitting. Okay. But better than saying underfit, overfitting, I prefer to talk about bias and variance because it's more concrete as a reasonment. There is another question. Is it possible, is it possible to have a low variance and apply correction term a posteriori to counteract the resulting high bias? Yes, we will see this, I hope, in the next class or in 2 classes. But yes, we will see that actually we can do something as suggested. Okay, so let's go into a little bit more details about the bias. So if you sample a dataset multiple times, so anytime that you sample a new training set, you will learn possibly a different model Y. So now take the expectation of all this model that you will learn, and this is the expected value of Y for predicting the input X. So the bias is actually what we have seen before. So the bias square is what we have seen before, the difference between the true function and the prediction of your model raised to the square. If you want to know the bias of your model, of course, you have to consider this not only in one point, but you have to consider the bias in all the input domain by weighting the bias square for the probability P of X, that is the probability of observing the input X. So this is actually the bias square of your model. So there is the integral over all the input space of the bias square in the single point X weighted by the probability that this input will happen. How I can reduce the bias square? The only way of reducing the bias square is actually increasing the size of the hypothesis space. And so increasing the size of the hypothesis space means consider more complex models. So talk about what we have seen so far. We have seen a linear regression. So if you have a linear regression, and suppose that you start and you have a very strong bias, what can you do to reduce the bias in linear regression or also in logistic regression? Yes, the thing that you have to do is to add features. So, yes, add features that, of course, in linear models means also add one parameter for each new feature. So in this way, by adding features, I add parameters, so I'm enlarging the hypothesis space, and so this hopefully will reduce the bias of my model. By doing this, of course, the risk is that you increase the variance. The variance is the difference between what you learn from a particular dataset and what you expect to learn. So the variance is the following. That is the same formula as before. So inside the integral, you have always the integral over all the input space, where you have a term that is weighted by the probability of observing the input. And the term is the variance. The variance is defined as the expected value between what your model will predict and the average prediction of your model. So if you have that your models trained with different realization of the training set predict very different things with respect to the average prediction of your model, actually it means that you have a lot of variance. How we can reduce the variance? Okay, of course, in the same way, in the reverse way that we have for reducing the bias. So to reduce the variance, we can use a simpler model. So less parameters, less features if we are in a linear regression. But with the variance, we have also another way for reducing this part of error, that is adding more samples. And adding more samples always works. Pay attention that adding more samples does not reduce the bias, but reduce the variance. So if actually you can access to a very large amount of samples, what happens is that you can allow for very complex models. Of course, this can be a problem because you can have the problem of computational problem, because if you have many samples, you have to train a dataset with many samples. Actually, this could be really complex. Okay. There is a question, what happens to bias with more samples? Actually, the bias is not affected by the samples. The bias is only affected by the size of the hypothesis space. It does not depend on the samples. Because actually in the bias you are already considering the average model prediction, and so this doesn't change. Okay, and so this is the case. So on the x-axis of this plot, you have the model complexity. So models that are simple have a large bias square, that is the red line, and have a low variance, that is the green line. As you increase the model complexity, increasing the model complexity means increasing the size of the hypothesis space, means adding more features, more parameters. What happens is that, of course, you are reducing the bias square, that is the red line, but in this process, you are also increasing the green line, that is the variance of your model. And since the error is what is the sum of the bias square, the variance, and the reducible error that, as we have said, we are not interested because the reducible error is constant with respect to the model complexity, and so is something on which we cannot operate. What we are interested is in the sum of the bias square and the variance, so the black line. And so usually the black line, we want to minimize the black line. Usually the minimization of the black line is not at the extreme point, so for very simple model or for very complex model, but is for some kind of model in between. And now our goal, we want to find this compromise. And so now we need techniques that allows us to control the model complexity. There is a question, in linear regression, when we realize, are we decreasing the bias? No, now we talk about this. So the question is, when we have seen that with a rich regression and lasso approach that we can regularize our linear models to avoid what? To avoid variance, because usually when you regularize means that you have used a lot of features. So a lot of features means very high model complexity. If you look at this plot, very high model complexity means that you have a lot of bias and small bias. And so regularization is a technique for moving on the left of the plot. So reduce the variance, introducing the bias. So regularization is a way of moving through this x-axis. In particular, increasing the lambda parameter, that is the regularization factor, you are moving on the left. But if you exaggerate, of course, the bias is too large. Okay, so actually we are, as you can see, as we have said at the beginning, actually all the supervised learning problem is synthesized by this trade-off and by finding the best compromise in this trade-off. Any supervised learning technique has one or more ways of dealing with this trade-off, as one or more hyperparameters or techniques for trying to find the best model complexity. Because actually the supervised learning problem is finding the proper size of the hypothesis space that you can afford given the amount of data that you can observe. This is the important thing. Why the machine learning problem is difficult? The machine learning problem, the supervised learning problem is difficult because you want to generalize over data that you have never seen looking at some data. But this generalization works if you have statistic evidence that you are producing a model that is robust. But so it means that you cannot afford to learn very complex models with few data because there is no statistical support for your prediction. And so finding the proper model complexity is actually this, is finding how many parameters, how large hypothesis space I can learn given the data set that I have. There is a question, is this plot the number of samples? In this plot, the number of samples is not considered together with model complexity due to higher computational power required. In this plot, we assume that we have a fixed data set of a number of samples that cannot be changed. If you increase the number of samples, what happens is that the optimal model complexity, that is the minimum of the black line, will move on the right. So the more the sample, the more you can afford learning complex models. But of course, you do not know how much complex the model can be given the samples. You need some procedures to evaluate what is the best model complexity, because there is a problem. You are not able to measure neither the variance nor the Bayer square. So you want to optimize the black line, that is the sum of the green line and the red line, but unfortunately you cannot measure this. You are not a measure. Up to now, we have not seen yet a measure of these two lines, because these are theoretical quantities. We have seen the definition of this quantity before, and okay, these are as they are defined. As you can see, they are integral over all the input space with the probability values, with the expected values of the models. Of course, all things that you cannot compute, because it would require knowledge that you do not have, the probability of over the x, making expected value with respect to all the realization of the data set. You have only one data set. So they are theoretical quantities that unfortunately you have not access to. But as we will see, we can produce estimator of these quantities that we can use to regulate the model complexity in our problem. And we do not use, there are also what are called the meta-learning techniques, that are techniques that try to learn the parameters of learning algorithms. Okay, so this is something that is currently a very active field of research. But actually there are also traditional ways of doing this kind of estimation. Okay, in order to understand how to measure or to estimate quantities that are related to the error that we would like to minimize, we have to start introducing some concepts. First of all, the training error. So given a data set D with n samples, you choose a loss function. For instance, for regression, we have seen that the loss function that you can use for training is the empirical mean squared error. That is the summation, is the average squared error computed over the training set. We have already said that this is not, unfortunately, is not the true loss function that we would like to optimize, because the true loss function is defined over the whole input space with the probability of observing the input. This is the empirical version, where I have samples from my problem and I simply compute the error of my model over the samples. So it's a noisy approximation of the true loss function. For classification, for instance, I can compute the average number of misclassified points. So these are train errors, so error that I observe over the data. And you know that if I increase the model complexity, so I add more and more parameter, the train error will always decrease. If you recall the example with the linear regression case, with the polynomial features, you can remember that we were able to put the train error to 0 when we use a number of parameters equal to the number of samples, because we found the interpolating polynomial in that case. And when I have the interpolating polynomial, the train error is 0. But you also remember that, okay, I have 0 error on the train data, but outside the training samples, the function is very crazy, can be very crazy. And so I'm not so happy, because of course I have put at 0 the train error, but probably what happened is that something else is no more so low, but is very large. In particular, increasing the model complexity, what is that goes to 0? The variance or the bias square? Yes, increasing the model complexity, you are reducing the bias, not for sure the variance. And so we can say that the train error can be a good approximation of the bias of your model. So when you measure the train error, you are somehow measuring something that is quite closely related to the bias. But unfortunately, is not able to capture at all the variance. So it's disregarding completely the variance. So by looking at the train error, you will always choose the model with the maximum complexity, because we'll overfit the data, we'll pass through all the data, and so is not aware that he is not generalizing over unseen data. So the train error is not a good measure of the general error, but only on a part of this error, that is the bias. What we want to predict is the prediction error, that is what we have called the true error, so the error where overall the input space. This is what I would like to have. And as you can see, by increasing the model complexity, while the train error, the blue line, always decreases, the prediction error, that is the error, the true error, actually, by increasing the model complexity, can, at a certain point, start increasing. You can see that when the model complexity is low, the train error and the prediction error are very close. And this is quite interesting, because it says that for simple models, the train error is a good way of predicting the prediction error. But when the model complexity becomes too large with respect to the number of samples that I have to train it, I have that the correlation between the two lines is lost. So using the blue line when the model complexity is large, using the blue line for predicting the red line is really unreliable. And so what we have to do is to consider an evaluation of the prediction error. And how we can evaluate this? We can evaluate this by splitting the data of our dataset in two sets. I have one set for training and one set for testing. So the training data are used for optimizing the parameters of my model, while the test data will not be used for optimization, will be used only for evaluating the goodness of the model that I have trained. And you see here what happens? You see that, okay, you have some data used for training, and again, for sure, increasing the model complexity, the blue line will decrease. And then I use other data that I have not used for training for evaluating the goodness of the model that I've learned. And as you can see, this is the black line that is noisy, clearly, because it's estimating from data. But as you can see, can stay around the red line that is where I would like, that is the line that I would like to measure. And I'm using the black line as a sensor, as a way of measuring the red line. Because I cannot trust the blue line, while the black line is, if you want, is an independent way of measuring the prediction error. So, by separating the data set in training set and test set, I have the fact that now the test set is an independent measure of the error. Why is it independent? Because it was not used for training. And so now the test error that I plotted, the black line, is an unbiased measure of the prediction error. Unfortunately, this measure will have some kind of variance, because you see that the black line oscillates a lot, because of course you have only a few samples that you have used. But now you have a problem. So you have the problem of deciding. Now this is a test set. Then we will talk about validation, but now we are not talking about validation now. We are talking about test. So I have a train set and a test set. So now the problem. In the previous case, I used all the data for training, and I have only the train error. Now I say, no, okay, you have not to use all the data for training. You have to keep some of the data away for testing purposes. In this way, you can measure, of course, the prediction error. Now, what is the problem in doing this? That now you have, if some of the data are used for testing, it means that the training set now is less samples. So you have less sample. And when you have less samples, what happens to the model complexity that you can afford? If I have less data, I can learn, yes, I can learn models that are simpler. You have said that the more the data that you have, the more complex are the models that you can learn. But if now I have to reduce the data because I need to save some data for testing the performance, it means that I can't use all the data for training, I have less data, and so the model that I will learn, unfortunately, will be less accurate. And so from one side, you would like to have as many data as possible for training, but if you use too many data for training and you left only a few for testing, the problem is that the test error will be really noisy, and so it's unreliable. And so now you have a trade-off. You would like, in the best world possible, you would like to have a lot of data for training and a lot of data for testing, of course, because you need a lot of data in both cases. But now you need to find a compromise, a trade-off for this problem. And we will discuss a little bit about this. There is no general solution to this trade-off. So how many data I use for training, how many data I use for testing. Of course, you need to have at least a number of test data that is enough to guarantee at the end that your model has good performances. Because if suppose that you have a classification problem, and suppose that your model has a performance of 0.8 using the test error. One thing is to say that your model has a performance of 0.8 plus or minus 1%. Another thing is to say it is 0.8 plus minus 50%. So in some cases it cannot be acceptable to have such a rough approximation of the performance. So in that case, you need to use more and more data for testing because you need to provide a reliable guarantee about what is the performance of your model. Otherwise, it's too risky to use it. Okay. So here is another plot where in the previous plot on the x-axis we have the model complexity, and we see with the model complexity the behavior that we have discussed before. If now on the x-axis we put the size of the data set, in this case of the training set, what you see is the following. You see that the train error, as you add more samples, the train error increases. This plot is with a fixed model complexity, so fix the model complexity and now increase the data. Of course, if I fix the model complexity and increase the data, the train error will grow. And this is quite reasonable to happen, because suppose again in the case where you had linear regression with polynomial features and 20 samples. If you have 20 samples and 20 parameters, you have a 0 train error. But now, if I increase the samples and I leave constant the number of parameters, the train error will increase, because I will see new samples and this sample will not well explained by the interpolating polynomial, and so I will see a train error that increases with the number of samples. On the other hand, we see another interesting thing, that while I increase the number of samples, the prediction error always decreases, because this is true. The more the samples that you have, the better will be the prediction error, because increasing the samples reduces the variance. And so, at a certain point, the red line will go down until it reaches the bias. That is the minimum that the error can achieve without changing the model complexity. There is a question. So this point suggests that at train equal to n test, right? No, here do not look. In this plot is not really important the size of the test set. Okay, what is important is the size of the training set. So on the x-axis you have the size of the training set. The size of the test set is whatever. It's not relevant here. The size of the test set. We are only discussing the size of the training set, and we say that when the size of the training set increases, you have that the train error increases, because the train error represents the bias, and the test error is a measure of the bias, and the test error will decrease, because the variance disappears when the number of samples increase. In fact, as you can see, when you have many samples, the train error becomes again a good measure of the prediction error. And so, and this is expected, this kind of behavior. Look at this plot. So again, you have on the, there is a question, so this plot represents the trade-off between variance and bias. In a certain sense, yes, is actually, it shows also the trade-off between bias and variance with respect to the variation in the number of samples. We understand better in this plot here. On the x-axis here, you have the training set size. And now you have this behavior. So on the y-axis, you have the error. And we have the blue line that is the train error, and the green line that is the test error. And the red line is, let's say, suppose that is a target performance that you would like to reach. Looking at this plot, you think that your hypothesis space is too large or too small? So we know the behavior. As this training set size increases, the train error will increase and the test error will decrease. This is known. But as we can see, the test error and the train error are quite distant. And so what this means? This means that it's too large, the hypothesis space. In the sense that if you have an hypothesis space that is small, as you increase the training set size, the test error and the train error at a certain point will become very close to each other. Well, in this case, you have increased a lot the training set size, and they are still far. So the test error is still much larger than the train error. This means that there is too large variance in your problem. And so what is the reason that you are considering an hypothesis space that is too large? This is another case where you have, again, the training set size, that you have the train error and the test error. Here you see that increasing the training set size, quite quickly you have the train error becomes really close to the test error. So it means that the hypothesis space is small. But as you can see, both the train error and the test error are quite distant from the desired performance. This means that you have a lot of bias. So you have chosen an hypothesis space that is too small, and the performance you are underperforming because you are producing results that are not so good. And so this is a case where the hypothesis space is probably too low. And so you can say, okay, I change the training set size, I look at this plot and say, oh, no, I need more feature for sure. While if you are in the case here, you say, no, this is too complex to be learned. Yes, it's not easy to say what is. Of course, you cannot. Usually you do not know the definition of desired performance, of course. But desired performance is something that you would like to have. Desired performance doesn't mean that is something that you can achieve. Maybe it's not achievable. But suppose that you have a desired performance in the sense that I want an accuracy of 95%, and you see something like what I see here in the plot. And so in the sense that you have enlarged the training set, you have the train error and the test error that are very close to each other, but your performance is 70%. And so you are quite far from 95%. So for sure here, you can afford more parameters, because when the test error is close to the train error, means that you are probably underfitting. And so you can enlarge the parameters. But when you enlarge the parameters too much, unfortunately, you may have a test error that is very much larger than the train error, and this means that actually you need even more samples. And so the question is, can you reach the desired performance? Can you reach the desired performance means, is the test error able to reach the desired performance? The question may have not an answer. But the important thing, beyond where is placed the desired performance, the question is, what is the relationship between the train error and the test error? When the train error and the test error are very similar, it means that you are in a case where probably you are considering an hypothesis space that is too small. On the other side, when they are very far the one from each other, it is a signal that you are using an hypothesis space that is too large. Okay, so how we can find a trade-off, how we can change the model now in order to find this trade-off between bias and variance. And so what we have to do is to do what is called model selection. So model selection is the topic of trying to search the proper model complexity in order to balance bias and variance. And we will see some approaches like feature selection, regularization, dimensionality reduction. And then we will see another set of techniques for managing the bias-variance trade-off. That is the one related to the model ensemble. And here is quite interesting to notice that actually model ensembles are an exception to what we have seen so far, because we have said so far that when I'm trying to search the model complexity, if I try to reduce the variance, I increase the bias. If I try to reduce the bias, I increase the variance. And so is actually a compromise difficult to handle. Model ensemble are meta techniques, so are techniques that can be applied to any supervised learning techniques that actually allow to reduce one of the two terms without increasing the other one too much. For instance, we have the bagging techniques that we will see that is able to reduce the variance without introducing too much bias in the technique, and the boosting technique that is able to reduce the bias without introducing too much variance in the model estimator. We will see this kind of techniques that are quite interesting for handling this trade-off. So let's start talking about model selection. So one problem that we have, as we have said, when we talk about finding the proper complexity of the model in learning, is the curse of dimensionality. Because unfortunately, the more is the number of parameters that you need to estimate, the more is the number of samples that you need to estimate them. And actually, there is an exponential relationship between the number of samples that you need as a function of the number of parameters that you need to estimate. And this, unfortunately, is very bad. Because, of course, if you want to reduce the bias, you need to add the parameters, but adding parameters introduce the needs of more samples. And this, in many cases, this is induce an exponential cost that translates in a very high computational cost, and also the cost of having the samples, because, okay, there are two costs, the cost of processing the samples, but also in some cases of having samples with the label, with the output, that not all the problem can be easily accessible. So, as we have already said many times, if we have a problem in the sense that we have not good performance with our model, adding more features seems like a good idea, but in some cases, if you are not able to increase also the number of samples, this will be actually not producing good result. In fact, what can happen is that if you have more features, what happens, the problem is that you can perform worse if you have not enough sample to do this. I try to give you an idea of the course of dimensionality. Let me try to do this. I try to share this. Okay. And so suppose that you have a segment between 0 and 1. So now, suppose that there is a region of this segment here, and this is 0.99. Okay. Now, my question is, if I take a point randomly in the interval 0, 1, what is the probability that this point falls in the region 0.991? Yes, there is 1% of probability. 0.01 is the probability, 1% is the probability that you will have a sample in this very small region. Perfect. Now let's try to do the same reasoning in a square. Okay, 0, 1, 1. You have this region 0.99, 0.99, and so now you have this region here. Okay, so now, what is the probability by sampling a point randomly, uniformly at random in this square, you will fall in this region there? You know that it will be 1 minus 0.99 square. Right? Because it's the area of the square, the full square, that is 1, minus the area of the white square, that is 0.99 square. So the area that is outside is 1 minus 0.99 square. Okay? And so now, if instead of 2 dimension I have 3 dimension, it will be 1 minus 0.99 cube. And if I have 1000 of dimension, it will be something like this. So now, what is the value of 1 minus 0.99 raised to the power of 1000? Is nearly equal to is nearly equal to 1. No, is equal to 1 because 0.99 raised to the power of 1000 is almost 0. 1 minus 0 is almost 1. So it means that if you have a 1000 dimension, the probability that you will sampling from this thin border of this high dimensional hypercube is almost 1. So there is actually probability 0 to sample inside it. And this actually is the curse of dimensionality. The curse of dimensionality sense that you are not able to explore. So for having probability of sampling the central part of this cube, hypercube, of course, you need to increase the number of samples a lot in order to have a sample covering this region. And so this actually is one issue with which we will have to take actions. Okay, so next time we will start looking at way of reducing the model complexity by doing feature selection, and we will see also how to manage this proper model complexity, what is the correct procedure for identifying the correct model complexity during our supervised learning problem. Do you have any question? Okay, if there are no questions, so thank you for the attention, and we will go on Thursday. The reason why in practice we shuffle sample is related to the separation of the test data set and training set. We have not already talked about shuffling the samples. We will talk of this in the next class. In slide 18, the model is too complex to be learned right. Slide 18, let me share again. Slide 18. In slide 18, there is no. So probably you mean 17. Because in 18 there is no case. In slide 17 you have the problem that there is too much bias, so the hypothesis space is too small, and y here is too large. Yes, 17. You have a different set of slides. Okay. Yeah. In slide 17, the problem here is that, as you can see, increasing the training set size, you have a train error similar to the test error, and so this means that you have an hypothesis space that probably is too small with respect to the number of samples that you have. Because, again, when the train error is tightly related to the test error, it means that you are enough samples with respect to the parameter. When the two errors starts diverging, it means that now the number of samples that you have is no more enough for the train error to predict the test error. Because what is the difference between the test error and the train error? Is we have said that the train error is more or less an estimator of the bias. We said that the test error is an estimation of the prediction error, so the true error. The difference between the two will be is the variance. Yes, is the variance, and potentially also the reducible error, of course, that you will have. But of course, since the test error is actually an estimation of the true error that you want to minimize, and the train error is an estimation, can be used as estimation of the bias, actually the difference between the two is the sum of the variance plus the reducible error. Could be possible to use test sample in training? No, we will see this next time. You cannot use sample in testing for training. We will discuss a lot this on Thursday. This is very important. You cannot do this. The next lecture is very important because actually we will deal about how to use the samples and how to test your algorithm. And it's very important because many people, even experts in this field, make very huge mistakes in this part. And making a mistake in this part means the risk of producing very bad results, because you fool yourself by believing that your approach is working. But actually, if you do some kind of mistakes that are quite frequent, actually you have no idea of the real performance of your approach. So it will be quite important. On a Thursday. Okay, I stop the registration. Bye-bye. There are other questions? For what concerns the question of Nicolas, that is related to if adding or removing features can help also in other techniques, the answer is yes for all the parametric techniques, while for non-parametric techniques we will see other kind of techniques. And Eugenio, could you quickly repeat the example on the course of dimensionality? Yes, of course, then you will have the registration, so actually you can review the example. But the example is quite easy in the sense that you take one dimensional segment and you say, okay, I split it in one part that is 0.99 and the other one that is 0.01. So sampling at random, there is only 1% of probability of ending in the small part. But if I now take this dimension and I increase the number of dimensions always by taking only 0.01 region in each dimension, the surface, if I increase the number of dimensions, the surface, the volume of this very thin region will be much larger than inside the region. And we have seen, because actually if you compute the volume, the ratio is very unbalanced. And this problem, the course of dimensionality, happens everywhere in machine learning, because anytime where you try to increase the number of parameters, you try to sample in a very large hypothesis space, you have the problem of the course of dimensionality, that you are always sampling on the border, never in the middle. And so if you want to sample also in the middle, you need to collect a very large number of samples. Okay. Bye-bye.